you could imagine different ways of traversing, going through this lattice to search for this frequent patterns, which means that finding this border between the frequent on the top and the non-frequent on the bottom by doing a search over the search space. The search could be done with methods we have seen so far, such as breadth first search or depth first search, or even a mix of both. So in the breadth first search, we're going to, as you know, go through each level one by one, and we won't go to the next level unless we explore all the item sets at one level. So we're going to start by the item sets of size 1, and then we combine those, only those frequent, to test in the next stage, and so on and so forth. In contrast, depth first search won't do the same way, but we'll go actually extend an item set by size until it reaches the maximum possible. So we're going to explore the item A. If A is frequent, then we're going to explore item AB. If the item set AB is frequent, we're going to extend it, and so on and so forth. If it's not frequent, whenever it's not, we're going to backtrack and check the combinations with another item. So it's possible to explore the search space in different ways in any search method we have seen so far. The a priori algorithm is what we call a level-wise algorithm. It goes level by level as it adopts a breadth first search on the lattice of possible item sets. So I start at level 1, which would be k equal 1 here. The idea is to generate candidates, check their frequency, generate the next generation of candidates, and so on and so forth. So the idea is to generate the candidates of size k. Suppose we are starting with the size 1, so we start with finding only the singletons items. So the candidates of size 1 will be a set of pairs, item set of size k, and the support of size ck, for which for all elements x included in ck, that's not empty, the support of x is bigger or equal than minimum support. So remember, the downward closure says that actually if you're trying to make a larger item set, any subset of this should be frequent. So any subset of ck, any x subset of ck, has a support necessarily bigger than minimum support, which means that we're going to create the candidates based on the smaller frequent item sets. Once we get our candidate, what we'll do is to scan the data set, go through all the examples in the data set to check the frequency of each candidate. So we're going to scan the data set to compute the support, and we're going to keep only those pairs, LK support of LK. L stands for large. Large in a priori framework means frequent. So I'm going to keep all large K item sets that have a support that is bigger or equal than the minimum support threshold we have set up. And then after that, these frequent item sets will serve to generate the next size of candidates. So I'm going to go back, but this time with k plus 1. So when we have k plus 1, going to use the frequent patterns of size k to generate the candidates of size k plus 1, and so on and so forth. So it's an iterative method that actually goes through the search space of the lattice line by line. Each time it generates candidates, it checks their frequency. How? By scanning the data set to calculate the frequency of each item set. So let's take our toy example again with the data set D. So recall that we had 5 transactions, AB, AC, CD, BCD, and ABCD. Suppose we set a minimum support threshold of 40%, so which means that we are going to be interested in all recurrent patterns that appears in at least 40% of your data set. All right, so at the first level of so remember, we start with the lattice of the empty size. So I'm going first to focus on candidates of size 1. So I'm going to check A, B, C, and D. These will constitute the candidates of size 1. These are the item sets of size 1, C1. We're going to scan the data set to see how frequent each of these item sets are. So for example, transaction 1 has AB. So for transaction 1, we're going to increase any item set frequency that contain A or B. So the A will increase to 1, initially started at 0, and the B will increase to 1. Transaction 2 has AC, so I'm going to increase the support of A to 2, and the support of C to 1, right? And so on and so forth. So at each transaction, I'm going to increase all the item sets that actually appear in this transaction. All right, so based on this, so the support is the ratio of the frequency divided by the size of the data set. So this will lead us to the frequency of the item set A being 3 over 5, B 3 over 5, etc. Given the minimum support of 2.5, I'm going to keep all of them. They are all frequent item sets of size 1. So the set of frequent item sets of size 1 will be each item A, B, C, and D with these supports. Okay, so this is the first level. So I ensured that I went through all possible candidates here, and I calculated the frequency of each of them, and it turned out that they're all frequent. So now I'm going to combine this frequent item sets of size 1 to make candidates of size 2. So the candidates of size 2 will combine A and B, A and C, A and D, B and C, B and D, etc. So for now, I don't have any frequency, so support. So the support for now is just 0 everywhere. I'm going to do another scan of the database to calculate the support of each of these item sets of size 2. So AB contains the item set AB, so I'm going to increase AB to 1. For example, the fifth transaction ABCD, we are going to increase AB, AC, BC, BD, etc. by 1. So we end up with the support of the candidates of size 2 being 2/5, 2, 1, 2, 2, 2, and 3. All right. So again, we look at the minimum supports we have, and we are going to prune all the candidates of size 2 that don't meet the support threshold. So in this case, I'm going to get rid of AD because it's not appearing frequently in the data set. And with a downward closure, if an item set is not appearing frequently, there's no chance that a larger one will appear frequently. So we're going to end up with the size, with the set of size 2 of frequent item sets of size 2. And the process goes on. We're going to do again C3. Here we're going to compare only those that have some head together, similar heads. So for example, AB and C are combined to make ABC. BC and BD are combined to make BCD. And this will ensure actually to have to create only candidates of size 3. So we don't want to combine, for example, AB and ACD because it's going to be a larger subset. All right. So candidates of size 3, I scan the data set and I compute the support again. I get rid of ABC, it's not frequent, and I end up with a set of frequent set of item sets of size 3. So the process seems quite easy when we talk about the toy data set we had with 5 transactions. But real-life data sets are really not like this toy example. The characteristics of real-life data set is that there are billions of transactions and tens of thousands and even millions of items. So think about, for example, the Amazon service that has actually lots of people using Amazon every day to purchase the items. And also, there are lots of items to choose from. So the reality is that we are dealing with billions of transactions, maybe millions of items, and which makes tera and terabytes of data. So this led us to actually, when we do the a priori algorithm, to have really a very, very, very deep lattice of possible item sets of a different level. And also which will lead us to do a lot of scan to calculate the frequency of all the candidates, which will actually also make the process very time consuming, given that we need to access the disk to make this calculation of frequency. And the other problem is that there is also a huge number of candidate sets. Remember, if you have a set of items I, if the item set is millions of items, you're going to have a lot of the size of the lattice, or the size of possible item sets is 2 to the size or cardinality of I. So it's going to be really a computationally expensive process to really uncover all the frequent patterns or frequent item sets in your data set that is very, very, very large. There are different kinds of representation of the transaction data set D that is proposed in the literature to make this frequency calculations and access and scan of the data set easier. So there are methods that actually adopt a row-wise representations in which we have, just like in other machine learning algorithms, we have the rows representing the examples, and each row has all the items in which that actually belong to the transaction. Other presentations are presented as a column-wise representation in which we have for each item we have the set of transactions in which it appears. Item A appears in 1, 2, and 5, the 5th transaction. And the last representation is a Boolean one in which we have the items appearing as features and the transaction identifiers appearing in the row. So for example, the item A appears in transaction 1, 2, and 5. Right? So given any of this representation, the algorithm then adapts to this representation in order to calculate the frequency of the item set. Recall the general framework in which we have a set of transactions D, from which we generate the set of frequent patterns F, and we want to generate now the rules from set of F. Let me mention first that extracting the set of association rules R is way less expensive than mining frequent patterns F. And the reason is that we don't need anymore to access the data set to calculate any frequency. All we will need to use is the set of frequent item sets and generate rules from that. So, however, the process still remains exponential in the size of the frequent item sets. Let me recall the framework. So given the set of frequent item sets F, and we have now another threshold, which is the minimum confidence threshold, minimum conf. We're going to generate all rules of the form left-hand side implies right-hand side, right? That are solid. For example, if we find this rule with a 20% confidence, means that 20% of items that are in a left-hand side are also in the right-hand side. Okay, so these kinds of rules have a confidence attached to them to express how strong they are. One way to generate the rules and avoid this, potentially another bottleneck in the, given that the process is exponential in the size of the item sets, we're going to generate all the rules in which we have the left-hand side is L minus C and the right side is C. So L is the frequent item sets. Remember, the a priori framework call it large when it is frequent. Okay, so I'm going to generate those rules and check their confidence. Confidence is this value here that actually is calculated based on the support of the item sets L divided by the support of the item sets L minus C. Okay, so if this exceeds the minimum confidence, then we keep it as a strong rules. Otherwise, we reject it. All right, so for a k item sets, otherwise in item sets of size k, we can generate 2 to the k minus 1 possible rules. So this is possible thanks to another property that was introduced by Agrawal and his coworkers. That actually means that if a rule with a consequence C is solid, then all the rules with consequences that are subsets of C are also solid. So we're going to see in the example how this property could actually help us just generate the rules that are strong. Suppose we have a minimum confidence of 60%. We start with the item sets that are frequent, so these are coming from F, right? So if we have this frequent item sets A, B, then we can generate 2 possible rules, A imply B and B imply A. We calculate the confidence as the support of AB, both AB, divided by the support of A. So that's how many transactions have AB among the A. Okay, so that's going to be 2 over 3. Is this rule strong? Yes, given that it exceeds the support of 60%. So I'm going to do the same thing for all frequent sets of size 2. The process goes on for every level of the item set. So for item sets B, C, D, we could generate CD implies B, BD implies C, etc. And also an item on the left side, D implies BC. And likewise, we are going to calculate the frequency, actually the confidence of the rule. CDB is the support of CDB divided by the support of CD. Okay, so in this case, we're going to keep all of them except this last rule here that don't have enough confidence to be kept as a strong rule. All right, this is how the process works. So you could see here that you're going to go through all the item sets and generate all possible rules and check just the confidence without access to the data set at all.